Hi, welcome to the first lecture of the second module of the course Data Science CS466. In this module, we deal with data science modeling methods. First of all, let us see the topics which we'll be covering in this module. There are mainly four main topics: choosing and evaluating models, memorization methods, linear and logistic regression, and unsupervised methods. In this video, we will be talking about the first topic, choosing and evaluating models. Under that, again, it can be subdivided into two: mapping problems to machine learning tasks and evaluating models. So let us start with mapping problems to machine learning tasks, under which we will be talking about how to solve classification problems, how to solve scoring problems, working without known targets, and problem to method mapping. As a data scientist, your ultimate goal is to solve a concrete business problem. Some examples are the increase in look to buy ratio, identifying fraudulent transactions, predicting and managing the losses of a loan. Many different statistical modeling methods can be used to solve any given problem. To make progress, you must be able to measure model quality during training. This is called as model evaluation, and also ensure that your model will work as well in the production environment as it did on your training data, and this is known as model validation. To prepare for these statistical tests, we always split our data into training data and test data. So this is the schematic model construction and evaluation. Our data set is split into testing data and training data. Usually 70% of the data is taken as training data and the rest 30% is taken as testing data. Using the training process, we make a model and use the rest of the testing data to see if our model is correct. Model evaluation means quantifying the performance of a model. Find a measure of model performance that's appropriate to both the original business goal and the chosen modeling technique. If we are predicting who would default on loans, we would have a classification task, and measures like precision and recall are appropriate. Instead, if we are predicting revenue loss to defaulting loans, we have a scoring task, and measures like root mean square error are appropriate. There are a number of measures the data scientist should be familiar with. We define model validation as the generation of an assurance that the model will work in production as well as it worked during training. Mapping problems to machine learning tasks. Your intended users of the model have a big influence on what methods you should use. If you want to know how small variations in input variables affect outcome, use a regression model. If you want to know what single variable drives most of a categorization, then decision trees. If you're trying to predict scores, then use regression. If you're trying to predict categories, random forest is probably a good choice. Solving classification problems. Here we see the example of assigning products to product categories. So we have many categories here: desktops, laptops, monitors, of which all come under computers. The next category is electronics. Under that we have games and stereo systems. Some common classification tasks are naive Bayes classifiers, decision trees, logistic regression, and support vector machines. Naive Bayes classifiers are useful for problems with many input variables, categorical input variables with a very large number of possible values, or text classification. Decision trees are useful when input variables interact with the output in if-then kind of ways, or they have a relation and relationship to each other, or they are redundant or correlated. It is easier for non-technical users to understand the decision processes that come from decision trees more than those that come from other classifiers. Logistic regression is appropriate when you want to estimate class probabilities in addition to class assignments. For example, in the case of probability of fraud in credit card purchases. Support vector machines or SVMs are useful when there are very many input variables or when input variables interact with the outcome or with each other in complicated ways. This is the example of a scoring problem. There are two types of transactions in this picture. In the first case, the delivery address is equal to the billing address, and in the second case, the delivery address is not equal to the billing address. So the first case, we can say that the probability of fraud is 5%, whereas in the second case, the probability of fraud is 90%. When we have to train data sets of situations with known outcomes, we can use either linear or logistic regression. Linear regression builds models such that the predicted numerical output is a linear additive function of the inputs. Logistic regression always predicts a value between 0 and 1, hence it is more suitable for predicting probabilities and rates. In some cases, we don't know what the specific output is going to be. In such cases, we may be looking for patterns or relationships in the data that will help us understand the customers or the business better. This class of approach is called as the unsupervised learning. Rather than predicting outputs based on inputs, the objective of unsupervised learning is to discover similarities and relationships in the data. Some examples of unsupervised learning are k-means clustering, a priori algorithm, and nearest neighbor. When to use basic clustering? K-means clustering is one way to sort the data into groups such that members of a cluster are more similar to each other than they are to members of other clusters. Suppose you find that your customers cluster into those with young children who make more family-oriented purchases and those with no children or with adult children who make more leisure and social activity-related purchases. Once you have assigned a customer into one of those clusters, you can make general statements about their behavior. For example, a customer in the with younger children cluster is likely to respond more favorably to a promotion on attractive but durable glassware than a promotion on fine crystal wine glasses. This is the example of clustering customers by purchase pattern and purchase amount. When to use association rules? Sometimes we might be interested in directly determining which products tend to be purchased together. For example, you might find that bathing suits and sunglasses are frequently purchased at the same time. This is a good application for association rules or even recommendation systems. We can mine useful product recommendations whenever we observe that someone has put a bathing suit into their shopping cart. At that time, we can recommend suntan lotion as well. When to use nearest neighbor methods. Another way to make product recommendations is to find similarities in people. For example, to make a movie recommendation to customer Jane B, you might look for the three customers whose movie rental histories are the most like hers. Any movies that those three people rented but Jane B has not are potentially useful recommendations for her. This can be solved with nearest neighbor or KNN methods, where k is equal to 3. Nearest neighbor algorithms predict something about a data point based on the data point or points that are most similar to P. This is the example of Jane B. Where we have k is equal to 3, we consider 3 neighbors of Jane B who watch the same type of movies that Jane B likes. So something that those 3 people have watched which Jane B has not watched can be recommended to Jane B. The last topic is problem to method mapping.